we go. We're cleaning things up today on having coffee. This was my project this morning. I just kind of gave it a little bit of a shine without changing anything too much. Let's take a look at that. Very interesting. This is platinum. That's what the white stuff is. And it's mixed with a little bit of gold. And it then becomes AuPt, and the platinum-rich end member of the AuPt family is black. And that's what you see in there, is the platinum and gold mixed together. And platinum causes the stuff to be black. Very interesting material. And the AuPt part of it is magnetic. The other part is too, I imagine, a little bit. And so they can make pictures with it to the folks that came before us. I hadn't touched this one. I just picked it up off the ground. My wife did, anyway. It's the same stuff. It's not quartz at all. Not even a little bit of quartz. It is platinum. Quartz, first of all, does not have planes of cleavage in them. When you see straight lines passing through a crystal, that's generally what it is. And that's what that is. And in fact, platinum crystals form in the cubic system, and they line up because they're all the same size. Platinum atoms are, and so they all line up in perfect little rows and columns. And the crystal structure is what you see here. The little cubes are not separate crystals of quartz at all. The cubes are the cubic structure of a platinum crystal. And they do, in fact, unlike if you had a conglomerate of quartz crystals, they would not ever line up in perfect little rows and columns. They just can't. They would be all different sizes. Okay, so they can't line up in perfect little rows and columns. Silicon dioxide itself only forms in the silica tetrahedron. Silica tetrahedron is a silicon atom surrounded by 4 oxygen atoms. It creates 4 3-sided faces. Triangles, right? 4 triangles. And it is the simplest of the platonic solids in geometry. The cube has 6 faces, and each section of these crystals is cubic. And they do, in fact, all line up in perfect little rows and columns. Let me see if I can find some better examples. See those faces there, those crystal faces? That 90-degree angle comes from just exactly what I'm talking about here. And you will find this 3-sided corner on isometric crystals. It's got the 3 axes, X and Y and Z. And the structure of the stone is lined up exactly with that. And look, there's like almost a checkerboard pattern across the entire stone. And it all lines up with that right there. Far out, huh? See, crystals are not accidental at all. They're formed because of the atomic structure. And in this case, it's platinum atoms lining up in perfect little rows and columns. And every once in a while, and it's a very regular once in a while, the black stuff incorporates some gold into the crystal structure. And that gold is bound in there with covalent bonds. So it doesn't act like a metal. When I try to run a current across this, it doesn't pass a current. In order to do that, I have to melt it. And platinum melts at 1768 degrees Celsius. So if I grind this up, I can melt it in my furnace. And it turns into the metal AuPt, because all of this will mix together, the gold and the platinum in the melt. People say, well, how do you separate it? The answer to that question is, why do you want to separate it? Because AuPt will do all of the things that platinum does with its hoppers on the crystal faces, and that's where the little black things are, where the hoppers are. And it will do all of the things that gold does, and in fact, it's more beautiful than either of them individually. And it comes in many different flavors because it's a solid solution series, which means there are different percentages of gold and platinum across a pretty wide range. But there are minimums, and the middle member, the middle part where it's 50-50, is magnetic. Because gold has one more proton than platinum does. And so that difference creates a north-south polarity. And that, in fact, is why you see the patterns in here, for part of that reason. And those patterns are created by the magnetic fields of the metal in the covalent bonding. But you can also see, look at that right there, you can see those little dots are lined up in perfect little rows and columns. This isn't separate crystals of anything. It's one single crystal of AuPt. This is where that microfine dust I find in the valleys of the basin and range geology here in the western United States. It's filled with this gold dust there, and part of it's magnetic, and I predicted that it would be there. And from that, I predicted that this would be here. And in fact, this is the granite that makes up the Sierra Estrella Mountains. I picked this up in one of the foothill mountains. Every mountain in the range is made out of AuPt. And you can see that cubic structure across this whole stone now, can't you? It's not a bunch of separate little crystals. It's one single crystal of AuPt. And in fact, the mountains I live in are made out of AuPt. And if you live in mountains, so are the mountains you live in. All mountains. Granite is not a bunch of separate little crystals. It's one big crystal of AuPt, and that's what mountains are. And look at the shape of this. See, this is like some of the mountains down in South America. They stick up and they look just like that.